hello together to the next statistics lecture. Yeah, we finished the last time the topic with confidence intervals, hypothesis testing. There we had our hypothesis testing with different distributions, normal distribution, of course, t-distribution, chi-squared distribution, and now, so to speak, we make a step back and we come back to a topic from the descriptive statistics, and this is the linear regression we want to start today. Okay, well, I think you already have seen this many times. In general, we have some data and maybe we have two variables, and these two variables, there we measured some different numbers. Here in my example, it is the number of orders and then the number of the volume of the revenue we made in euros. So the first data point is that, let's say in the first month we had 2 orders and we had a revenue or a volume of 36 euros and so on. And now we want to know, is there any dependence between these two variables, order and volume? And well, quite often a good choice is just to look at the data, not only at the table, but to take some graphical representation, and this we will do right now. So we just make a scatter plot. On the x coordinate we take the order, and on the y coordinate we take the volume. And this I started for you in Excel. So this is our order and our volume, and then you just mark it and take the scatter plot xy, and so we obtain from a graphical point of view a nice thing. Oh, I should do this in another way because otherwise it is not scaling. And there, not very surprisingly, we can more or less say that if we have here up, no, order, and here volume, that we can make the assumption the higher the number of orders, the higher is the volume. And why is this our assumption? Well, not very surprising. If we look at these data points, we more or less just say, well, let's fit some kind of linear function into this data, and then we see if we go to the right, we have to go upwards. So, and what we want to discuss today is how should we fit this line into the data? And this will be the topic today. Well, since we also want to calculate how to fit this line into the data more or less by hand, we will do it in Excel, but in a very slow way, because I'm not convinced to give you just the formulas, put it in, and you are done. I think in the beginning you just should do this very slowly, that you really understand again what you are doing in this point in statistics, and not only saying, well, I somehow fit in here data, and some guys 100-300 years ago they invented some formula for this, and well, okay, this will be okay, and I do it in the same way. And therefore, in the next step, we take so to speak, smaller example, that we say a company wants to know, and this is again some kind of hypothesis, but in this part we only do the descriptive analysis. In the next course, in the next semester, we will do also hypothesis testing on linear regression. But here we want to talk about how to fit this line into our data, so that one company wants to know how their sales, their revenues, volumes depends on the visits of their representatives. So they have some representative, they walk around in the town or in the region, and there we collected some data during the last years, and we found that if we have 9 visits, our volume will be 24. If we have 11 visits, it will be 33. If we have 5, 10, and so on. And maybe in this company, the people are discussing, should we offer some other people a new job? So if we increase our visits up to 30, this means we need some new guy, some new representative in our company maybe, and this means we have higher costs, and therefore we want to know, we assume, of course, that the more visits, the more volume, but is the higher sales volume, is this enough to pay another new guy? So this will be a general question in many companies. And from our data, we want to have a clue, is this a good decision to increase the visits? And we know that the increase of these visits means also that we have higher costs. So, a step back, then we ask, in general, we have again 2 variables, and we assume that they have some dependence, and we want to analyze this dependence between these 2 variables in a very general way. And for this, we distinguish these 2 variables. We say one variable is independent, and we have a reaction of the dependent variable y if our independent variable x is changing. And in general, therefore, we call this variable x the explanatory variable. And this means a change of x implicates a change of y, maybe up or maybe down. Oh, this is my old German version. So this put me out of this. Oh, where is it? There. So this linear regression then defines an empirical relation via a linear function. So this is maybe the easiest way how to assume some dependence between these two variables. And this I think you know from school. A linear line could be maybe f of x is 3 plus 2x, or in general we have y is a plus bx, and there a is the point on the vertical axis, and this is the slope of the line. If this is maybe here 2, then it means if x increases by 1, then y increases by 2 times 1 is 2. Not very difficult. Okay, and then we can look how could such a dependence look like. And of course, the most easy dependence is shown here. And there my question. I have to start the chat. Here we are. So how would you fit if you have these data points, the red data points or the blue data points? How would you fit here a line within these data points? Let's start with the blue lines, the blue ones. If you just look at the vertical axis and the horizontal axis, then you see here, if I go one to the right, how much do I go up? Blue data means 3, of course. So delta x, if this is x and this is y, delta x is 1, then delta y is 3. And if we look at these data points, this is always the same. True for all data points. And if we assume a linear dependence, f is y is a plus bx, if we have made this observation, can we then already say something about a and b? You have an idea? Here's always 1, 1, 3, 1, 3, and so on. If I put in here a line, there maybe I can use this one here. Up, up. It's possible. Yes, great. Super. Mm. No. So, yes, of course, B is 3. That's my mouse. Mouse. Up. There it is. So, then, up. Then, of course, we have B is delta y over delta x is 3. And you have been going further already, because then you just extrapolated this line here, and this line, of course, then cuts the vertical axis at a equals 2 and a equals 2. And in order not only to draw it here and determine this graphically, we of course also can insert in our assumed linear dependence some data point, and some data point is 2 and 8. Some data point x2 and y is 8. We already know that b is 3, so we know 8 equals a plus 3 times 2, and then of course we obtain a equals 2. Of course, this is not really difficult, and if we do this for the red points, what we obtain there for A and B. Here, if we go one step down, we have to go 2 steps to the left, and again we see this is always the same. 1, 2, 1, 2, 1, 2. It's also fit by hand. Some line. If I go 1 down, I have to go 2 to the left. What slope? Which slope has my line? Oh, this has moved here, right? One half? Is it really one half? Just think about it. 1 down, 2 to the left, minus 1 half. Of course, we have a negative slope. So minus, now it's moved back. I don't know why. So then I have to do this again. Back again. So, and here, so we have minus 1/2. And for A, well, we already see it, that it is 20, but this is only done by hand. So by hand, this could also be that the true point is 20.1 or something like this. But again, we can insert some data point. This data point would be x equals 2 and y equals 19. So we have 19 equals a plus minus 1/2 times 2 is minus 1, and 19 plus 1 equals 20. So this star here comes from this data point. For example, you can actually use any data point you have given. So 19 equals a plus minus 1/2 times 2 is a minus 1 minus 1, so we obtain a is 20. Well, if you have collected data like this, then of course you don't have to think really in a theoretical way how to fit here a data, because here you have more or less a one-to-one, 100% dependence between 100% determined dependence between two variables. But in general, we will have some scattering cloud around our data, as we have seen here in my started sting example. And now we want to go to this example here, where we want to answer this question I've posed some minutes before. So, and if we have a scattering cloud, we have to ask how to fit our line. And for this, we make this assumption that given our independent data point of x, we want to find, so to speak, good numbers for a and b in order to estimate from this independent variable some theoretical value for our dependent variable y. And these two parameters or coefficients a and b we have to calculate from our collected data. So this number will be on the regression line. And by chance, this can be equal to our collected data point of y. But these two values do not have to coincide. And since they do not have to coincide, then we more or less we speak that by fitting our data with a regression line, we make some error. And the difference between our theoretical value and our collected data point, this we call epsilon, and this is just the difference between our theoretical value and our true value. And here should be also, this is our error, which we make by the assumption y hat a equals a plus b xi. So maybe not that surprising is that we want to determine a and b in such a way that the quadratic differences, so epsilon squared, will be minimized. So aim is the sum of epsilon I squared I from 1 to n. N is again our sample size to be minimized. So, and where come these squared from our minimization? So for this, let's go back to our scattering cloud here. So let's just say this was our first assumption by hand. Then the difference between our collected data and our line is this distance, is this distance, or is this distance. So, and at first we say, well, we want to fit our data somehow into this cloud that these distances should be as small as possible. But if we take only the distances, then this distance here is positive and this distance is negative. And if we just sum these distances up, then this value positive, this value negative is reduced by each other if we just sum this up. And for this, more or less, we can say, well, let's take the square, because if we take the square, then we have no problem anymore with plus and minus. But then we could also take the absolute value of y minus y hat. This could be also possible. But the square has also one really nice property. So y square, let's just take a new slide here. So this is our optimizing problem. So y this square. So at first we can say no problem with plus minus in the difference y minus y hat. But this plus minus, we could also, this would also vanish if we take just the absolute value, y minus y hat. But how does the absolute value of some number looks like? This looks like this. And this has one not very nice property, because at this point, if the absolute value is 0, so in case that our collected data point and our theoretical data point, if they coincide, then this function is not differentiable anymore. So we have no derivative. So no f of x, f or f prime of x, sorry. No f prime of x. So, and why is it not very nice in our problem to find something like an optimal line if we have no derivative? Why is it not that nice? What do we quite often do if when we are optimizing in economics? Hmm? We quite often take just the first derivative, setting this to 0, calculating the numbers, and then we have our optimal point. But if there does not exist any derivative, then our procedure to obtain the optimal values is not that easy anymore. So therefore, we can say that maybe a second point that we choose this square is that this is differentiable. So y minus y hat is differentiable, and the absolute value y minus y hat is not. But these two things are more or less only some practical issues. And the third is then maybe also a philosophical reason for this. Think about the normal distribution. How does a normal distribution look like? This was 1 over f of x 2 pi sigma exponential power of x minus mu over sigma squared. And we know of the really great importance of the normal distribution. And the normal distribution has in its density function this quadratic difference from the mean. And therefore, taking here also the quadratic difference is directly connected with the normal distribution. So that this quadratic difference is so important, this comes, so to speak, from the importance of the normal distribution. Connected, with the normal distribution. And we can also say, but this we cannot do in this course, this is also connected then with the so-called maximum likelihood fit in a very general way. So, and yeah, quite often in statistic courses, you just only say, well, let's minimize here the quadratic error, and there comes out some formula, and then we start to do many examples. And I think that you also should think about what you are doing, because all what these two things here, this could also be possible if I take the sum over the error with respect to an exponent of 4. This has the same properties which I need for 1 and 2 here. But then I'm leaving the normal distribution in my calculation. But on the other side, if you go further in statistics, then you of course think also about this exponent of 4. This is then called the method of moment, that you go up from 1 to 2 to 3 to 4 to 5 and so on in order to analyze your data. But we take a step back. So hopefully I really motivated for you that we take the sum of the squared errors, because this you do not find quite often in statistic courses. Oh, this we wanted to do together today, because this you also did not find quite often, is how do we obtain our formulas. Oops. And this we will do together. Let's move this a bit up here. Because we now have just here a function with two variables. And this I told you, if you want to optimize this, we just take the first derivative and then we set this first derivative to 0. So let's start. df with respect to the parameter a. Where do we find a? In here. But we also have the square at this point. So at first, we have to take the 2 in front. This means sum over I from 1 to n, 2 times yi minus a plus b xi. And then we have the inner derivative minus a, and the derivative of minus a with respect to a is just minus 1. So this times minus 1 Has to be 0. And then we have here our 2 in front of the bracket. This minus 1 times 2 is minus 2. This should be 0, so we can multiply by minus 1/2. And then, of course, we obtain sum of I equals 1 up to n of yi minus a plus bxi equals 0. And if we take df with respect to b, then again we have this outer derivative, so I up to 1, 2 times yi minus I plus bxi. But now we have this function, b times xi with respect to b. What is the first derivative? So if x of b is bxi, then we have f prime of b equals, so b is our variable and x is some number. Some idea? So you can think of if xi is a number, let's say 5, then you have the function f of b is 5b. What is then the derivative with respect to b? Let's take it here. F of b equals 5b. Then f prime of b equals, this is just 5. So from this we just obtain xi. So again we have to write here xi, and we have also this minus sign. So minus 1. Again we can multiply by minus 1/2, and so we obtain sum I to 1 yi minus a plus bxi, but now times xi equals 0. So, and then we just look at these two conditions. These are the first order conditions in order to obtain an optimum. Let's take one. There, this is a sum. Here we have a minus and a plus, so we can divide it, the sums and the differences. We can take the summations just in front of y, a, and bxi. So here we obtain sum of up to n xi equals sum 1 to n over a plus sum b xi I from 1 up to n. And now hopefully you also see this. This is just the sum over all data points of y we have collected. And if you think what is the arithmetic mean of these data points, this would be just this sum divided by the number of the sample size. And therefore we obtain n times y bar. Remember, y bar is just 1 over n I1 n yi. And this equals, what is this? Observe, a is a fixed number, maybe 5. This I think we had in the beginning of our lecture. Sum of I is 1, 2, 3 over the number 5 is summing up 3 times 5. 5 plus 5 plus 5 is 15. Here we have to sum up a n times. So we just obtain n times a. And here, this is a fixed number. Again, this we can put in front of our summation. And so we obtain, let's put it here, b times sum over xi, I from 1 up to n. And this, of course, we can also write with the arithmetic mean of our collected data points for x. So this is then just b times n times x bar, since x bar is nothing else than 1 over n times the sum of all xi. So we find this is n times b times x bar. And then, of course, we see that we get rid of the number of the sample size. So we obtain y bar equals a plus b plus x bar. And this is maybe not a very surprising result, since this just means that the data point of both arithmetic means of the dependent and the independent variables lies on our optimal regression line. So this means the data point x bar, y bar is on the optimal regression line. I think I need another slide. Let's take this up here. This we do not need anymore. And now we go to our second condition. And for this, we just multiply here our brackets, and then we obtain for 2 sum I is 1 up to n of xi yi minus a times xi and minus xi bxi, so minus bxi squared. And this has to be 0. Then we have here just differences, so we can write in front of these two differences our summation sign. So we obtain I up to n xi yi minus, this is a constant, this can be put in front of our summation sign, a xi and minus, this is also a constant for our summation, so b times xi squared up to n. So, and now we are almost done, since from 1 we have obtained x bar equals a plus b, y bar equals a plus b x bar. So this is known and this is known. This we can just calculate from our sample set. And therefore, we obtain a equals y bar minus b x bar. And this we just can put in here. Because what do we also have? This is a known number. This is a known number. And this is a known number. Here in the summations, we find only our data points. And here we can more or less say that this is x times y, and then I make the bar above both variables. This just means take your data points, multiply x1 times y1. This is a new data point. x2 times y2 is a new data point, and from this new variable, you should take just the arithmetic mean. So n times the arithmetic mean of a new variable x times y. This is again just only n times x bar. And this is more or less the same like this, but not x times y, but x times x. So times n b x squared, and now the bar has to be above the squared, because this means you should multiply xi x1, for example, times x1 at first, and then you take the average of your data points. And here I lost some A. Again, the n cancels out, and we insert here this value for our A. Then we obtain bar minus y bar minus b x bar. In front we need 1a minus a times minus b x squared, and the bar has to be above the squared. So, and this you just have to solve for b. So we obtain bar minus a y bar minus b times a times x bar minus b x squared bar equals 0. Then you have here and here. Sorry, here I did something wrong. What did I wrong? This has to be, do not have to be an A, but an X bar, of course. Sorry. X bar and X bar. X bar and X bar. And we have here another error. Minus times minus means that we have here a plus sign. Okay, collect this further. This means x times y bar minus x bar times y bar equals, and now we put this two terms with the parameter b on the other side. So we obtain b times x squared bar. X bar times x bar means minus x bar, and now the squared out of the procedure of taking the average. And then we have b equals x times y bar minus x bar times y bar over x squared bar minus x bar squared. And then we could put this into this definition, into this condition. So put this in 1, and we obtain for A equals y bar minus x y bar minus x bar y bar over x bar squared. Sorry, the bar has to be above. X squared bar minus x bar squared, and here is another x bar. So, and now we are done. We have, this is known data. And of course, this is known data. And I think, well, this is a calculation over 2 slides, but it is also only a calculation over 2 slides. And this is, I think, also quite often not done in statistic course. And we have here some kind of advanced statistic courses. So I think I have to go a bit further when I'm explaining you the linear regression, because otherwise you would have seen only this slide here. Well, this is our optimizing problem, maybe, but also not quite often in statistic courses. You see just the first order conditions, and then you say, well, oh, this is so complicated with these summations, and what do I have to do, and so on. And then you only just obtain these two formulas here. That this large formula here is your solution for the point on the vertical axis, and this is your solution for the slope of your regression line. But what we have done is just that these two numbers are nothing more than that these two numbers can just be calculated by calculating in advance some average values. So which average values do you need? We need x bar, we need y bar, we need x y bar, and we need x squared bar and x bar squared. And if you have these 6 numbers, you can just put these numbers into your formula and you are done. And also, this maybe you have already heard in other statistic courses, is that if we define the so-called covariance as the sum over the product of both differences from the mean. So the difference here of x from the mean of x and here from y to the mean of y, then you also can show that this formula becomes even more simple, that this is just covariance over variance of x, and you are done. And here again, from this formula, you also see some deep dependence to the normal distribution, because this I've shown you is just this part of the squared difference in the density function of the normal distribution. And if you have a multidimensional normal distribution, then of course you also need in the description the covariances of your variables. And maybe this is a more deep motivation of this linear regression. So then what we more or less do is just, and this is the picture of our example here, that if we now take these two formulas we have obtained from our optimizing process that if we then just calculate A and B, we obtain for A in our example 1.97, this is B, sorry, 1.97, and for A 3.91. And this line just minimizes the sum of, so to speak, all these red squares, I from 1 to n. Oop. No, here we are. Okay, here I've done this for you. And now, of course, I told you that we should just calculate this at least with one example, more or less by hand, but I do not want to do this with you via a calculator, but let's do this in Excel. So where is my Excel file? This is here. And we need this one here. You can see the Excel file? Okay. So, this shouldn't be here. Yeah. So what do we need? We need, as I told you, X bar and Y bar. For X bar and Y bar, we just sum it up. Oops. Oh, this is German. So, Summe. And then we obtain the mean is 70 over the sample size, and the sample size is just 6. Or let's take it up here. N equals 6. And then we take is this over 6 and F4. And then we find X bar is 11.67 and Y bar is 27. So what else do we need? We need X times Y bar. So what do we have to do? 9 times 24, we put it in here, 11 times 33, and so on and so on. So in Excel, this is just 9 times 24, 216, 11, this one, this one, this one. And we need also the sum of all these numbers. And what else do we need? We need also, so here, the mean, then we Divide this also by 6, 355.76, and we need x bar, x squared bar. So we have at first then to calculate 9 by 9, 11 by 11, 5 by 5, 25, 169, 400, and 144. Of course, this we can also do here. So this equals 9 squared, 11 squared, and so on. We also have to sum this up. And then also take the mean of x squared bar. So we obtain 156.78. 156.67. So, and one last number we needed, this was x bar squared. How do we obtain x bar squared out of our numbers? Well, we already have x bar here, 11.67. So 11.67 squared. So we also need, let's take this, here, x bar squared is then this squared. 136.11. 136.11. So, and with these numbers, we go into our formula. I think this we get today. We can do today. So this is our formula for our parameter b. So we have done b equals 355.67. This is x times b squared above both variables minus the product of these two numbers. This we also need. So let's take this here. This would be then, or here, x bar, y bar is this times this is 315. So we obtain x bar times y bar is 315. So minus 315 over, we go into our formula, x squared bar minus x bar squared. X squared bar is 100, and so this is x bar times y bar, 100 56.67 minus 136.11. So this is x bar squared, and this is x bar. So x squared bar and x bar squared, and this is then roughly. This I also do in Excel. What do I need? I need then b equals small b equals opening the bracket, then 355.67 minus 315 divided x squared bar 156.67 minus x bar squared 136.11. Enter. Oops, there's one bracket missing. And the bracket missing is here. And whew, this is the number we have already seen. Our B is 1.97. And A we just obtain by y bar minus b x bar. This is roughly 97. So we obtain for A, y bar was 11.67 minus b is 1.97 times x bar was, oh sorry, the other way around. Y bar is 27 and x bar is 11.67, and this is then approximately where we are here. A is equaling y bar 27 minus b times x bar, and is 3.92. 3.92. And then you are done. So, written much, therefore it takes a bit. So then I end the lecture.